This is Unit 7, Video 10 on buffers. Buffering solution is a solution that resists change in pH. Very important in biology. All biological systems, including us, have buffering capabilities. So when you have a buffer solution, you can add base to it and it'll consume it, prevent the pH from changing significantly. You can add acid to it, it'll consume it and prevent the pH from changing significantly. So very little change. Now the key to a buffer is going to be it's always made of a conjugate acid-base pair. So if you remember, conjugate acid-base pairs are any two chemicals that differ by H+. Classic conjugate acid-base pair that we use for a buffer is ammonia and ammonium ion. Now obviously we can't put ammonium ions in solution, so this usually would come in the form of ammonium chloride. Ammonium chloride, but being an ionic compound, when it hits water, it's going to fully ionize. We're going to have a solution there. Here's our beaker. So in our solution, we're going to have ammonia and ammonium ion. The buffering components, the conjugate acid-base pair, are not going to react with each other. Okay, and that's the key. They're going to react with any acid that's placed in the buffer, any base that's placed in the buffer. Now, being a conjugate acid-base pair, the component that has the extra H+ is the acid. The component without the extra H+ is the base. So I have an acid and a base both present in the solution. So if I go in and I add a strong acid like HCl, when I put the HCl in there, it's going to selectively react with the base part of the buffer. The base is going to neutralize the acid, and we get a little change in the pH, but not significant. On the other side, if I add base, sodium hydroxide, into the buffer, I'm going to get a reaction with the acid component of the buffer, which would be the ammonium ion. The chloride, in all cases, is a spectator ion. It's just floating around. It's in there. It's just floating around, doing its own little thing. So let's write some reactions. If I add, let's start with the HCl. I'm going to add the HCl into the solution. It's going to react with the base part, so that's going to be NH3 plus HCl. And this is a type of double replacement reaction, but here the H+ is being donated to the NH3. Obviously you have to make ammonium ion, and so we're going to get NH4, which is what that makes, and then Cl. Well, being aqueous, we can tell this chloride is going to be a spectator ion, so we can write the net ion equation, which is always better to see. NH3 plus H+ goes to plus NH4 plus. And this is the reaction that's taking place in the buffer anytime we add any acid. It could be nitric acid, it could be sulfuric acid, whatever it is. We'll get different spectator ions, but we'll get the same net ion equation. Now what about the base? I'm adding the base in. The base is going to selectively react with the acid component of the buffer. So I'm going to have NaOH plus, in this case, the ammonium ion. I'll write it out as ammonium chloride. This is a double replacement reaction. The ammonium ion is going to switch with the sodium ion, and so I'm going to get ammonia. You're always going to make the conjugate of whatever we're using in the buffer. So the buffering components are always on opposite sides of the air. So I'm making ammonia. I'm also going to make water, and I'm going to make sodium chloride. Now you look at this, you can say, okay, clearly the sodium and the chloride are my spectator ions. So the sodium and the chloride are the spectator ions because these are all strong electrolytes. So I'm going to have hydroxide reacting with ammonium ion, producing ammonia plus water. And that is the reaction of that component of the buffer. So in summary, conjugate acid-base pair, they both have a part to play in the buffer. The base is going to neutralize any acid you add. The acid is going to neutralize any base you add. These two are not going to react with each other, so we can keep them in the solution together at all times.